All right. Hi, everyone. Welcome to our afternoon session for the MIT Robotics and Climate Workshop. I hope everyone enjoyed lunch and all the morning sessions. So in the afternoon, we'll be moving on to our panel discussion for the climate science section. So sort of building off of Abigail's talk earlier this morning, we have three amazing scientists that span the climate science space, and they'll be talking to us today and having a discussion about robotics, observations, machine learning in oceanography and beyond. So I think first off, why don't we all just go down in a row and just introduce ourselves and sort of maybe our research and what kinds of data we use, perhaps. So yeah, Alice, you want to start?
Okay, hi. I'm Alice Thuren. I'm a postdoc at MIT-WHOI Oceanographic Institution, and I work with autonomous underwater vehicles to make observations of the oceans. Specifically, I've worked in the California current system and also in the Gulf Stream. And most recently, we measured warming of the Gulf Stream in the past 20 years, and we used the Argo float program, which are also an autonomous underwater vehicle, and also the Spray underwater glider, also an AUV for that.
Hi, everyone. My name is Bianca Champenois. I'm a fourth-year grad student in mechanical engineering. My research is more on the modeling side of things and data analysis. So I think big picture, we like to ask questions about what kinds of data do we need to make models, and what is it more important to prioritize? Is it making simulations or collecting data? And then how do we make models that combine those things? But then more focused, we like to apply a lot of our problems to ocean and atmospheric problems. So we've looked at ocean acidification, microplastics, and we've also done a little bit of work on this new hot topic, which is related to machine learning for climate and weather prediction.
Okay, hi everybody. Thanks for having me. I'm Lukas, a fifth year in the MIT-WHOI joint program. So with EAPS up here at MIT and then Woodsell Oceanographic Institution down on Cape Cod. A physical oceanographer, mostly doing observations. So I'm the person that envies all the data that a modeler has, being able to compute all those gradients. It's much more data sparse otherwise. We focus on the coastal ocean because that's where really a lot of the biology happens. Like the coastal ocean cover about 10% in area of the world's oceans, but have 50% of the productivity. So it's that's first of all where all the communities live, and then secondly as well where a lot of the biology happens. And so we use ocean robots like autonomous underwater vehicles and ocean gliders to get a better understanding of how offshore open ocean forcing affects coastal oceans, and then as well the physical conditions that then drive ecosystems.
Cool, great. So maybe a first question for everyone, and feel free to answer whoever is sort of when all of you sort of use data of various types and sources, what does that process look like, taking the data that you just received from your instrument or robot or from an online data set and transforming that into interpreting climate phenomena or oceanographic features? Sort of where do you feel like some of the messiest parts are? Are there a lot of quality control? What does that look like for you guys, I guess?
Yeah, I would say, first of all, it's a privilege to be able to go out in the ocean or to receive in situ observational data. I think Abigail kind of touched on in some ways how rare these observations are. And the first thing we generally do is a quality control round, but also with autonomous underwater vehicles, we try to make that as efficient as possible because we want a lot of them at the same time. So I would say we go through a very standard sort of routine, and in our labs, those are just optimized for efficiency so we can get through it. And then we actually try to put our distributed data onto a regularly mapped grid. And so we create products that are kind of a model will give you a regularly gridded solution. We try to also, from our observations, produce a regularly gridded product, and then you do science on that.
Yeah, so I work with a lot of different types of data sets. I guess the biggest ones, we work with a lot of numerical simulations that include observations. So those are called reanalysis. And those are really great. They're really high fidelity, high resolution, but they're also really expensive and really big. So we do have to do a lot of reduced order modeling on those. And so that's more on the simulation side, but then also on just the observation side, we work with in situ observations, which we just don't ever have any in like December and January. We work with satellite data, which when there's clouds, you get a lot of gaps. So you have to figure out what to do with that. And then we also just, it was quality control and stuff. And so when you're including data in a model, you have to do some uncertainty quantification and propagate it. So a lot of different challenges associated with the data.
We do something actually fairly similar than what Alice has described. So it's like when you have a 3D feature, particularly like on the smaller scales down in the ocean, like you take an ocean robot and that goes across. So you can kind of like fairly easily with like fairly established algorithms nowadays get that gridded across that section. The issue then kind of becomes what just happened upstream, what just happened downstream. And I think like that's kind of where there's a lot more uncertainty. Of course, like you can try to put another robot in upstream or downstream, or try to take it out and let it go another upstream section and kind of get an idea about how your entire field evolves spatiotemporally, and then do some objective mapping on that, let's say. But of course, that will smooth out your gradients, particularly, and thinking about like how fast your system evolves. It's just what kind of this big question of what scales or what processes do you actually now resolve. But I think like it's actually more and more important to kind of go from this 2D going across something into learning more about how the system looks kind of in both 3-dimensional space and time. And that's kind of a challenge there.
So I think Bianca touched on this briefly, but this idea of uncertainty and error, I guess I wondered if any and all of you wanted to touch on how you propagate and consider uncertainty when your measurements may, disagree with each other or are noisy. How does one interpret that as being noise in the system or error in the instruments that you do, and sort of what are the is it sort of an art that has to be done to sort of deal with that?
Yeah, so my answer for this is actually, and then I got distracted by the second part of your question. Okay, so but my first part answer is that a lot of the uncertainty, the largest uncertainty in observations, is due to the submesoscale and mesoscale field that Abigail was talking about. And so we generally try to make our observations to average over that. Like the ocean is a complicated turbulent fluid from small scales to extremely large scales. So a lot of what we do in observations, we have to understand that inherent variability that exists. Many ways to this, but averaging. So that is our biggest source of uncertainty. A lot of our instruments now are extremely, extremely precise, such that you can neglect that uncertainty in light of the natural, we call it the natural variability of the oceans. The other thing I will say, though, is a lot of the new sensors that are coming on that are doing biogeochemical variables, so things that are going to measure CO2 in the oceans, ocean acidity, nitrate, those sensors are all new. And when you have a new sensor, what we actually spend a lot of time doing is calibrating them. So actually all of our BGC sensors right now, there's a lot of work that needs to be done to make sure that they're making climate scale accurate observations.
Yeah, I guess I can answer kind of more on the modeling side, because we get the observations and we trust that they're been calibrated and that they're as good as they can be. But I think just on the modeling side, we've been doing a lot of the standard UQ methods that are popular these days. So a lot of Bayesian methods, a lot of ensemble methods, whatever is in the literature these days, we've been trying and comparing to other state-of-the-art methods. But I think one of the hardest things is when you make a model and maybe you're assuming something about the climatology or whatever, and then maybe there's some big event that happens, some extreme weather event or some climate, temperatures increasing, then your model's all wrong. And do I trust the model? Do I trust the observations? So I would say that's one of the biggest challenges.
I feel again, reiterating what Alice was alluding to before, it's like particularly on the physical parameter side, really precise. And I think like there are a lot of uncertainty is really coming from how we use our data and how we interpret the data. It's like kind of, I think like a lot of when we do a transect, we really interpret that as being taken a snapshot, kind of like, okay, this is like taking a transect across a model field. But if you put an ocean robot into the ocean or go somewhere with a ship, you will automatically alias, because you're not taking a snapshot, you're not taking measurements across a front at the same time, but you're kind of slowly moving across. At the same time, you have tidal fields acting on that. And so it's like your field evolves while you go across. And so I feel like a lot of the uncertainty is coming from moving, like not really taking a snapshot, but in the end, often interpreting it as one, and that is something that needs to be considered. And so, yeah, averaging works as one potential solution. The issue arrives when you try to really like resolve the strong gradients, and are actually really interested in the gradients and don't want to smooth them out.
Can I? I'll just add one thing,
Yeah.
which is when we work with data assimilation, what those modelers want is both the value and the uncertainty in the observation. And so that is something we're able to provide in, almost all cases. But like a very concrete example of what you're asking.
And then on the biogeochemical side, I think it really makes the point why humans still are required to be in the loop right now. I feel like we can, like particularly ocean gliders can be out for about 2 to 3 months right now. So there's actually kind of the idea to just let them go off the beach and then they come back. Particularly in the coastal oceanography, we can actually do that, and it's like really valuable to have fairly continued monitoring that way, because like the range in time is so long. But something that's really missing there is the validation part, particularly when it comes to the biogeochemical data, where it is just important to go out as well and take a sample, bring it back into the lab, and actually check, does the nutrient data that comes from our biooptical sensors, is that really as well the nutrient data that is there in a water sample if I collect it at depth.
Yeah, that's awesome. So Alice, I think you and Lukas sort of touched on this idea of like what's resolvable with the instruments and the field campaigns that we have now, and what isn't. And sort of, I guess specifically, what do you think is the smallest, most important like scale that we can sort of get with current technology? And are there hopes of resolving some of these more complex features that Abigail's was talking about with actual field campaigns and observations in the future? Is that something that we can maybe hope that robotics innovations can help us improve on?
Yeah, it's difficult to do the observations in the ocean due to the multi-scale nature of the problem. One thing that I would say is I work with a lot of instruments that are focused, that we use them in the way we're focused on persistence. So we're focused on observing there 24/7, 365 days a week for years and years and years and years. With that method right now, we can do mesoscale to large scale. So mesoscale's like a characteristic scale of like a little bit of a larger turbulent type scale. And that's about like 10 to 100 kilometers in size. For smaller than that, we do have the technology to get at sub-mesoscales, but we can only do it in a very small location, right? Like a small region right now. And really the challenge, I think, both on the modeling side and on the observational side is getting from centimeters to thousands of kilometers, which is essentially what we have to do.
Yeah, I feel like if you put a sensor into the ocean, like we can sample on a 1 second scale in that regard. So we can collect actually data like really extremely regularly, and we can as well have an ocean mooring, let's say, with a profiler that just goes up and down and allows us to really continuously measure it in a single location. I think though, like, and that really makes it possible to look at, let's say, internal waves, which are not surface waves, but waves between 2 different density layers. So it's like waves within the ocean, and they happen more on the subtidal scales, so really just over hours. So that is possible. I feel like what's really issue with like this sub-mesoscale nature is that it gives us a 1D picture. We are really in one location, and now it kind of becomes a problem to think about, okay, what happened a kilometer upstream, a kilometer downstream, and that really speaks for having these big campaigns out there that use a lot of assets. There was recently a campaign called S-Mode of California that combined a lot of different instrumentation. They had airplanes flying really deep over the ocean and take, like, from there we were able to get the sub-mesoscale field at the surface with a really unprecedented resolution. And then from there, both ships and ocean robots, they then targeted certain fronts. So that was kind of, I think, like one of the biggest campaigns to really like get to this 4D nature of things. But again, we were kind of a little bit biased towards what happens up in the upper ocean in the mixed layer, and biased towards what's observable from space, because it's just really hard to look into the ocean and get the data there.
So Bianca, I know you sort of straddle the worlds of maybe ocean climate science as well as computer science, and we touched a little bit on this in Abigail's talk, but do you find that there is difficulty sort of bridging the two, that the language and the methods and that, you know, marrying the two, or that there might be places where they disagree on sort of how they do things? What is that process like?
Yeah, I don't think it's disagreeing. I think it's a lot of like if you go to the CS community, there's a big trend in like AI for climate and stuff, and there's a lot of really good work going on there. But a lot of it's kind of already exists in the oceanography community, and maybe is using different language or vocabulary, or, you know. So I think there is a lot of work to be done just to purely translate and bridge the gap between the two communities. So I think that would be exciting to see.
Yeah, that'd be great. Yeah, I also want to see if there are any questions in the audience for the three panelists right now. Yeah.
I'll just shout it.
Yeah.
What do you all do to handle the lack of data at depth? Right. If you say like we have all this data on the surface, right? But obviously we care about like what's going on in all three dimensions. Like, how do we handle that?
Yeah. And I'll repeat the question is, what do we do about the lack of data at depth? Sort of, you know, we have satellites at the surface, but, you know, the farther down we go, the less data we have, and sort of how do we remediate that, I guess, in all our different fields? Yeah.
So yeah, I have observational data to 500 or to 1,000 meters. So that's the type of data that I collect. Below that, there is I guess you could say it's autonomous, but there's a float program. There's a deep Argo float program that is going to come online. And there are also moorings that can be full water column depth, so down to 4,000 meters. And potentially some other technologies, but those I think are the most used for sort of what's going on in the abyssal ocean.
I can answer kind of on a different scale. I look a lot of, one of my projects was looking at kind of most coastal waters for aquaculture. And so when we talk about depth, we mean more like 100 to a few hundred meters. But still, it's really hard to get measurements there, especially if you're trying to keep the costs low because you're not a scientist, you're just in aquaculture industry. So some of the methods we've used are to develop like a high fidelity numerical model and then to train some sort of machine learning model to predict subsurface properties from surface properties, assuming there is some, you know, physical relationship that the machine learning model can capture. And then you can use satellite data or more inexpensive surface data, and we've seen a lot of success with that. So I do think, like, you know, bridging the modeling, the heavy numerical modeling, fluid mechanics with machine learning and with observations, you can do a lot of nice things with that.
Yeah, I think I personally needed to learn to be very deliberate about the problems I aim to solve with the data on hand, and just kind of acknowledge that with observations alone, it's just hard to tackle certain problems. And I think it was really interesting to kind of make that experience throughout the PhD, because like all your classwork is about kind of how you can nicely resolve everything, and everything in the ocean like physically relies on computing gradients. But if you have an ocean mooring, you measure in a single point. So computing a gradient is basically impossible. So it suddenly becomes somewhat descriptive. And it was just interesting to bridge from kind of this class work understanding of, oh yeah, I can like theoretically understand the system with Navier-Stokes to, okay, how does the data actually look like in the ocean? But I feel like when looking into dynamical physical oceanography, like really connecting or finding the synergies between high resolution ocean modeling and observations is really, really valuable, because like particularly from regional models, then we can like as well somewhat inexpensively go towards a 1 kilometer resolution without having petabytes of data sitting somewhere. That then makes it possible to compare that with observations, and we were able to learn some stuff from there, from kind of having an observation first in descriptive space, kind of in like, oh yeah, we see a salinity signature somewhere, and the question is more like, where does it come from? And then you go into modeling space and try to like kind of fill the gaps that the observations have.
Vivi?
You could pick the observations that you want to have, like what would you sort of try to gear those towards? Like I think this room is called Robotics. Like our goal is to try to get you those observations that you think like can't be captured with the current technologies. Like are there sets or like areas that you think we should be focused on, or like anything like that? Do you have any insight to that?
I would personally just like to be able to resolve gradients better. And I feel like that's really about ocean robots communicating with each other. I feel kind of like having several assets in the water at the same time, like some upstream, some downstream, and kind of thinking about, okay, they keep the same distance, they kind of time well to each other to kind of get a more 4D picture of the ocean for a particularly small area. I think that would be really fascinating. A second part, we have recently experimented a little bit with an ocean robot that was able to identify a front by itself and then follow it. And it was really interesting. It worked semi well, but I feel like thinking about how much capacity there is on the human side to like check on your ocean robot the entire time, kind of like every time it surfaces, to look at the data day and night, and then go back and kind of program where it's supposed to go. That requires a lot of resources, and there are not that many graduate students out there who can do so. So I feel like we talk about autonomous underwater vehicles, and I feel like we could talk about what autonomy really means here. Like, does autonomy mean I need to tell it where to go every single time, or can it make decisions by itself to follow certain frontal parameters, or kind of to target certain features in the ocean and follow that, perhaps even like with a fleet of vehicles? That would be amazing.
I can share a similar kind of need. Like if there was a robot that every time there's cloud coverage and the satellite's not picking up something, then the robot would go. Or whenever there's heavy rainfall and so there's a spike in the acidity, in ocean acidity, then a robot would go. Like whenever there's like a need, and then the rest of the time, I feel like we just send out cruises and that's great, but it's not always targeted to like a specific event or need that we want. So
yeah, so my opinion on this issue is what we really need is low cost. And I'll give you some numbers. So the Argo Float program, each of the core Argo floats, if it's a BGC Argo float, is $100K, mostly due to the cost of the sensors. An ocean glider is $250,000. And for a really knowledgeable surface vehicle, like the one that WHOI just built, I think it's called the Mayflower, it's in the multiple millions. And so what we really want to do if we want to measure the oceans by actually putting instruments in is we need thousands of instruments. So right now the core Argo float program has 4,000. And that monitors once every 300 by 300 kilometer box. If you want to measure, like, okay, I've been giving these numbers out to people because, so I looked on Wikipedia. If the Earth is 70% ocean, that's a surface area of 360 million kilometers. If you put one thing in every 100 by 100 kilometer box, like the low resolution model Abigail just showed, you need 36,000 instruments that can also profile to depth. So we have a major issue right now of cost, And we need both low cost and highly reliable, because the ocean is a really tough place to be. There's so much pressure, and really these things can't leak, essentially. So from the engineering and robotics side, that's what I would like to see, because right now my opinion is we already have the ability to make these 4-dimensional observational products, but there's no way we're going to fund that through our NSF proposals, right? And it's probably arguably not worth it. But if we were able to, one, reduce the cost of these instruments, make them extremely reliable, autonomous, we would have that ability. And then the other side of it is the sensors. The sensors right now are also quite expensive. I think in general as a field, we're making these not at scale right now. So if we were able to make them at scale, we'd actually be able to observe the oceans.
Seems like a common theme through all this is quantity, quantity, quantity. We just need more observations. So I guess going on to, sorry, were you gonna say? Yeah.
And then it's like, speaking from our perspective, like, I mean, WHOI is one of the largest ocean institutions in the world. Like now thinking about, like Abigail alluded earlier to like what happens in the, like across the world that isn't the North Atlantic, that's already sampled extremely well, particularly like thinking about monitoring programs in coastal communities around the world that perhaps relies on fisheries much more than we do for our protein resource, particularly in the global south. Like that's, I think, like one region that would be really worth targeting with like increased monitoring.
Yeah, I feel like cruises are like great opportunities to sort of go out and sample a feature or an area of interest, but sort of the cost with even just setting all that up is just really not feasible at scale. So yeah, it seems like that's what a lot of everyone here is alluding to. Yes, you have a question back there.
Yeah, so I guess that question for me is the customer, for, say a company a startup comes out with a really efficient and cost-efficient robot and can sell these ocean robots to people, are the customers mainly academic institutions like WHOI, or is there anyone else that would be willing to buy ocean robots? And what's the like private case?
Right now, which is just very new and very hot, is marine carbon dioxide removal. And I see in the near future a big market there. Right now, I think of what I'm doing as a race between what I'm doing and what the private industry might want to do. And I think I will get there faster, actually. I don't know. But they have that need because they're saying we're going to measure the carbon going into the oceans. And it's so remote. And so mostly what they rely on right now are models. But I do think that they might have the money to invest in actual observations as well to back up, like, how much carbon credit am I going to say that this particular action is related to.
A question that I have on, like, kind of following up on this quantity question is, to what extent can you balance between, like, if the cost of the sensors are driving a lot of the cost of the platform, if you want a low-cost platform, are there sensors that you could sacrifice in the name of coverage and then get, like, more higher quality samples sparser and, like, infill, or, like, how would you handle that trade-off between quantity and quality or breadth of data?
I can give a quick answer. I think you definitely can make trade-offs. Like if with modeling, you can kind of infer some properties from others, and it's not perfect, but depending on how precise you want it to be, you can get good estimates. But that's from the modeling side of things. You can definitely make some trade-offs.
I would as well say that, like, from the physical perspective, you always need temperature salinity to then get to density and to then, because that drives the dynamics. But I feel like there are, like, currently two big companies out there on the market, Seabird and RBR, which produce these instruments. That's a really non-saturated market, I feel, for the world. So I could imagine that a third company going into that space could actually just, through competition, already reduce prices there.
And did we have a question back there, or?
This is somewhat related to the quantity question. I'm just curious, is there, when you deploy robots in, like, our surface world, we sometimes consider its interactions with like maybe nature, maybe with humans. Is there ever a concern that with these autonomous or semi-autonomous robots that go underwater, impacting the underwater biodiversity in some way? Are you concerned about that as well? Should that be taken into account when designing?
I guess, that's a great question because I've never thought about it. So I'm going to take a second to think about it. But I think that in general, with what we're putting out in the ocean right now at sort of in these sort of global programs, we're not really seeing negative impacts to biology. Most of these objects are either floating with the currents or moving very, very slowly. In fact, they tend to attract barnacles and create a small ecosystem on them in terms of these underwater gliders, and also sort of any moorings as well. So I haven't thought about that closely, but my guess would be that we don't have any sort of negative impacts right now that we are causing.
I think as well, like I recently heard that actually for the Argo program, which is a program that's like there's not a ship that takes them out of the ocean at some point. They kind of just die at 2,000 meter depth. So there are some out there in the ocean, and there are some ideas to like reduce the plastic amount in there to not contribute to ocean plastics that way. Which I mean, like since we are in science, we should, in my personal opinion, really like we should focus on that. But compared to the economic scale of how much plastic lands in the ocean through non-science pathways, it's really just a drop in the bucket.
And I guess sort of when we're talking about accessing and gathering more data from the ocean, do any of you, or what are your experiences with sort of data access and sort of sharing the data and the community communications with it? Is that part of the challenge as well with sort of interpreting the climate signal from these? And yeah, I guess to get your thoughts on sort of sharing or accessing other people's cruise data and things like that.
I will say, so the instrument that I use, the spray gliders, all of our data is publicly available and you can get on websites. It's also incorporated into the GTS, which is what models pull from to do real-time forecasting. But I will also say that I have definitely interacted with other groups doing cruises, and sometimes it's just hard. And like, I'll say it in a way that, so when I was a grad student, there was a lab and they just had so much unused data. Like you could be a student in that lab and you could do your whole PhD with no new data collection. So yeah.
I can confirm that. I feel like there's a lot of data out there, and we write NSF proposals and then we go out and then we write the paper about the easiest story that's out there. But there's more data out there that can be analyzed. I think there's I feel like there's a good way of how data is shared from long-term time series, like when we have ocean moorings out there that are there for a longer time. I think that there's really been focus on sharing that data publicly. Like I work a lot with the Ocean Observatories Initiative data, which was funded by NSF. It was actually didn't fund the PI. The entire project was to fund the Ocean Observatory system. That was then publicly available immediately, through telemetry data. And it was as well, the idea behind it was to allow researchers that don't have the access to the sea as easily as the big ocean-going institutions to use in situ data. And I think that was somewhat successful. But going out on cruises, there's just so much, particularly on these adaptive sampling cruises where you make decisions of where to go immediately while being at sea. It's difficult to go through that data set even when you are in the group if you haven't been around during that shift. I feel like this is one of the issues, sharing that data.
Bianca, what's your experience been with sort of accessing satellite data, like observational data, and trying to incorporate that into your models and such?
Yeah, some data is really easy to get, and there's very nice websites and APIs to get everything. And then other data sets, like I said, I work with more local coastal aquaculture industries, and we actually like have to pay for our data sets, and like my advisor always tells me like each data point is $250. So I'm like, okay, let's use these well. So I think there's like they both said, there's kind of both sides to it.
And I guess we can imagine that maybe that might change as the private industry becomes more and more interested in the ocean and the ocean subsurface. Sorry, question? Yeah.
Lucas, you mentioned earlier that you want to see something like multiple robots working together to get like a 4D like time sync map across the ocean. How important is it that you have that time synchronization, and like so what's your window? Because it's very difficult to get robots communicating underwater.
It depends a little bit on the scale, but if we're thinking about like this kind of kilometer sub-meso scale, I think like we're talking about like the field changes within a day. Like that's kind of the time scale we are talking about. So it's like, I think particularly when we talk about ocean physics, we don't even need to know exactly where we are like on the dot. I think like that's more of a problem when we do coral reef monitoring or something that's really like extremely small scale, or with aquaculture, we really like want to know how much is the distance to the aquaculture exactly, versus if we're thinking about transient features already, I think that's not that important. But yeah, we're talking kind of about an objective map that is able to resolve changes on the kilometer scale on a one tidal cycle, like within 6 to 12 hours. For me personally, it's again like that's just the problems I think about, like when we think about kind of the sub-meso scale. But there are other problems which like I'm much more interested in the small scales. So.
Bianca, is there sort of a refresh rate for the satellite data that you use that sort of is like, I wish I could get higher resolution to resolve this weather phenomena or extreme event?
Yeah, I think the satellite data is really good for like the whole Earth, but when you're looking at, an aquaculture industry in a very small region, like first, if it's 1 kilometer satellite, it's okay. 4 kilometer, 10, like then you're just, your whole region is 1 square and you're like, okay, 1 temperature, but you're like, that's not what it is. But it's still like helpful and useful, and it's still useful, but they're definitely depending on what you're interested in, the scales can be very tricky.
Yeah.
I kind of had a follow-up question on that, specifically from Bianca. Have you used like hyperspectral cameras on satellites before, and like what data can you get from that, and what is missing that you really need like local observations?
Yeah, I haven't done that much work on like actual satellite data processing. I kind of just take what NASA has on their websites. They have very nice API to get temperature, chlorophyll, like all these nice things. But I know that's like a really big field of research because I'm getting the data from NASA and I'm trusting it, but it maybe that it's not calibrated correctly and there's some other problems with it. So that's all free, yeah, and it's very easy to get. It's a very nice website for that.
Alan, you have a question?
How much do you think your research agendas are shaped by the data that's already out there? Like, if we didn't have this data, would your research look differently? Does that make sense? It's a weird question.
Yes. Yeah. I feel like I have I'm coming from the observational side, and I'm now started to use models, but I feel like from the observational side, it's really like the questions are shaped by the data that's available.
Yeah, I think a really interesting question that my advisor and people in my lab like to ask is like, what data is most valuable and like what data do we need? And then, you are still working within the constraints of what you have, but I do think that is kind of an interesting question to pursue. And it's like, because we're working directly with this aquaculture industry, we can make targeted observations based on, okay, we think there's going to be some event here that might contribute to this, and then so let's go put a sensor there and see what's happening. But yeah, it's a really hard question, and we do what we can with what we have.
I would say I was lucky enough to be in my PhD group was called the Instrument Development Group. And so we kind of do those things hand in hand, right? We think of what we can achieve, and then we build or we try to design the thing that's going to achieve it. So yeah, I was just lucky enough to be a part of that.
Did you often find you needed new sensors?
Well, so I'll say this, though. The lab is currently run by someone who's trying to do persistent observation, and we're currently essentially targeting mesoscale and large scale with persistent observations. So in order to achieve that, we had to actually make measurements for a very long time. So like currently, there's like approaching 20 years of measurements for one particular method. Right, because we're saying, can we measure the ocean at these long time scales and like mesoscale to larger, so like 100 kilometers type spatial scales. So I guess what I'll say is like, so that lab right now is focused on this particular method that they developed 15 years ago, right? Because we're actually doing the measurements to see whether that correctly can do all these mesoscale phenomena. So like one of the things I did in my PhD was I looked at subsurface eddies. And that's almost sort of one of the core goals of that whole idea of using gliders in this way.
And I think it kind of touches as well on this element that perhaps supplements this idea of more, something that could work as well as longer, kind of to think about something that can be out for a longer time. Like I know that there are now people thinking about like docking stations, put out basically a charging station out there to an ocean mooring. And of course the robot needs to know where they are exactly, because that would be really cool for long-term monitoring, because I think we are currently as well somewhat restricted by the timeline something can be out, depending on, of course, like the payload you put up onto the platform.
Yeah, and I can imagine that has a huge implication for trying to understand the response to climate change, which is such a slowly evolving signal that you want a long duration time series. Things like that.
With a lot of variability on top, kind of on other scales like seasonal cycle, tides.
Yeah, for sure.
And I'll push back a little bit on the more, longer. I think it's more like, observed to some extent, at least for me. It's like observed to some extent, and then when you see something happening that's abnormal, then go investigate and like add and then do more. But like for a lot of things you can kind of. Yeah.
And I think one of the major scales in the ocean is the Rossby scale. The Rossby scale is about 10 to 100 kilometers. There's a lot of very interesting basic science and physics, in my personal opinion, happening on scale smaller than that. But for a lot of the energy, the Rossby radius of deformation, the Rossby scale is appropriate.
Cool. So I will end with one final fun question for all of you. So assume a mysterious philanthropic source decides that the projects you're working on are very interesting, and they decide to give you $5 million to sort of do as you please, sort of either a field campaign or developing new sensors or anything, or even look at new data sets or train new models. What would you like to do with the sort of $5 million, sort of no questions asked, for your scientific research, the questions that you're interested in?
I'm thinking about trying to observe the formation of something called subtropical mode water. It's formed just south of the Gulf Stream, and it fills about the top 600 meters of the ocean. And so I would just use my $5 million to buy probably 3 gliders and and then fund all of the work to go into putting them into operation.
Yeah.
Maybe I'll buy 4.
Okay. I used one.
But that's important for how fast the ocean is warming. I think there's some indication that it's not just the surface ocean, but down to maybe 1,000 meters is warming much faster than we had anticipated. And the ocean is a big heat pump. So it stores heat and it transfers heat. So if you say instead of 100 meters that we're heating it very quickly to 1,000 meters, that's a multiplier by 10. So I'm really interested in mechanisms by which that may actually be happening right now.
Very cool.
Yeah, I have, I guess, less. I'm just more interested in kind of modeling with data that we have. But I think for like, let's look at aquaculture and ocean acidification. I think it'd be awesome if I just paid someone, and whenever I want a data point, I could say exactly where, when, and how deep, and what, and they would just go and get it for me. That would be great.
Yeah, how far does 5 million go? But I feel it would be really interesting to get better in navigating under sea ice, and be able to track what comes out of Greenland glaciers, like glacial meltwater. So it's really interesting to think about how does the meltwater from Greenland end up in the North Atlantic, because like that, depending on where it ends up and with how much stratification, that really determines on a global scale how much of this overturning happens with the Atlantic meridional overturning circulation. So it's like would be really interesting to have to map a particular fjord really well, and then have a robot be able to know where it is based on the bathymetry, and be able to go under the ice back and forth for a season, to kind of get a full year picture of that and see the seasonal cycle of the water mass transformation.
Very cool. All right. Do we have any more questions? If not, let's give our panelists one more round of applause.